Business Stats 226. Now that we have completed quiz number 1, we need to move on to chapter 4, where we're going to study a bit about probability. We're looking at a Venn diagram here, and the important thing to remember is that everything inside that yellow line represents 100% of all probabilities. In this case, we've got the blue representing 60%, the 10% plus 50%, and an overlap with the orange overlapping from 30% to 50% for a total of 80%. There'll be lots of questions on that, and we'll learn a bit later in the chapter how this is a useful tool. Probability. It's a number, normally a percentage, between 0 and 1 that measures the chance or the likelihood that some event will occur. If it's 0%, it means it'll never happen. If it's a full 100% or in a full 1, it'll happen all of the time. So we've got basic probabilities. We have an experiment that we have to produce. We have an event, which is a collection or one or more of these outcomes. Sample space from an experiment in which full collection of outcomes is gathered. And we've got 3 different types of approaches. Classical, where we're assigning probability based on the assumption of equally likely outcomes. Relative frequency, assigning probabilities based on experimentation of historical data. And subjective, and I refer to that as a guess. The important thing here is that the sum of all of the probabilities has to equal 1.0 or 100%. A further definition of the classical approach: the probability of an event is going to be the frequency or the number of outcomes favorable to an event divided by the total number included in the experiment. An example would be when you're rolling a die. You've got 6 possibilities that can come up. That means your probability is 1 in 6 of a specific number coming up, or in this case, 16 and 2/3. The relative frequency approach, it's based on historical data, if you recall. It's just the total number of observations divided into the total number of times that a particular observation occurs. An example would be the inspectors at Bay State Manufacturing conducted checks on manufacturing process at the final assembly. In the 25 assembly units, the following number of defects occurred. 0 defects happened 6 times, down to 4 defects happening twice. So the probability of each is found by dividing the total number of units divided by the total frequency. You first need to take the number of defects. There were 6 times that it occurred. There were a total of 25 observations. 6 divided by 25 is 24%. When we've gone through all of the defects, total number of frequencies, we get 100%, or 1.0. Simple probabilities, an example: what's the likelihood of a single event? If you draw from what's your chance that you're going to draw an ace from a deck of 52 cards? It's 4 divided by 52. What's the chance that you're going to draw the ace of spades out of a full deck of cards? It's going to be 1 in 52. Another example, a container holds 5 balls, rubber balls, 1 large red, 1 small red, 2 large blue, and 1 small blue. So the probability of a red, 2 out of 5. Probability of a blue is 3 out of 5, or 40% and 60% respectively. Conditional probabilities. Let's go to the example. What's the chance of a second ace given on a condition that 1 has already been drawn, drawing an ace on your first draw from the deck, and then drawing a second one? You've got 3 chances remaining out of 51. Remember, 1 ace has been drawn. You've only got 3 left, but you've also got only 51 cards left. So it's 3 divided by 51. We're dealing with no replacement of that first ace that was taken. Statistically independent. I'm leaving that as a separate slide because it's a quiz question. 2 events are said to be statistically independent if the occurrence of the event has no influence or the likelihood of occurrence of the second. Going back to the color and size of the rubber ball, they're statistically independent. 1 large red, 1 out of 3. The other example is 40%, 2 out of 5, where they're both red. 40% means they're not statistically not independent. General multiplication rule. We're going to go back to the card example. If we're going to draw an ace out of 52 cards, it's going to be a 4 divided by 52. That times the second draw, which would be 3 of 51. The math on that is going to be 12 over 2652, or about 4%. For independent events, they're both going to be 4 out of 52, or just under 6%, or a little bit higher probability for the multiplication out of independent events. The Venn diagram, we talked a little bit about that on the first slide. Remember, the total yellow represents 1.0. That includes the circles. In this particular case, we've got internet shoppers. They purchase airline tickets. 80% of them did. That's event A. 0.3 plus 0.5 equals the 0.8. 60% of them bought books online. The 50% plus the 10%. And then 50% purchased both. So this said, let me ask the question, how much space is left outside of the orange and red circles? The answer is going to be 0.3 plus 0.5 plus 0.1. Subtracting that from 1.0, it's going to be 0.1. In this chapter, we're also going to look at tree diagrams. We're going to look at different options under separate stages. In this particular case, we have said that 25% of the project's performance is under budget. Likewise, 70% is over budget or not under budget. Stage 2, second project being evaluated, 60% of the time it's under budget, 40% not. When A was not under budget, it is indicated that 20% of B is under budget and 80% is not. When we look at percentages now, all options have to add to 1%. So how do we get the 0.15 off to the right-hand side? We're taking 0.25 times 0.6 equals 0.15. We multiply each of the branches out, and when we add those all together, we have to equal 100% or 1.0. Probability trees. Especially helpful when the experiment involves multiple steps or stages. We assign probabilities to the various branches. Each branch represents a possible outcome. And remember, adding all the probabilities together, we have to equal 1.0. Now, counting outcomes, multiplication, combination, permutation. First of all, multiplication. Simple process. How many outcomes to a multi-stage experiment? I put an example down at the bottom. If we go into the store to buy a shirt, we find the shirt in 3 different colors. We find them with 1 button and 2 buttons, and then 4 different sizes. How many different types of shirts can we buy? Simple multiplication method says 3 times 2 times 4. We've got 24 different options available to us. Combinations. How many different 5-card hands can I get with the normal 52-card deck? Here's the formula for this. Number of experimental outcomes when X objects are to be selected from N objects. I haven't worked the math on that, but it's N factorial over N minus X factorial times X factorial. That will give you the number of combinations of X. Take an N one at a time. That brings us to the end of Chapter 2. Best of luck. It's actually a fun chapter.